All right, let's talk about something that every single one of us in the RF world has to deal with. How do we move beyond just guessing and start actually engineering systems that are predictable and reliable? Let's get into it.
So, just so you know where we're pulling this from, everything we're about to cover is straight out of part 16 of a really in-depth 20-part series on RF propagation by the folks at RFI Detectives. And look, it's designed for us, RF technicians and engineers. So let's dive right into the core issues you're facing out there.
Okay, let's get right to the heart of it. The engineer's dilemma. We have all been there, right? You're out in the field staring down an RF problem that seems to make absolutely no sense. It just defies logic. And without the right tools, it really feels like you're just taking shots in the dark.
I mean, does this sound familiar? You spend hours and hours putting together a link budget, but deep down you know it's really just a very educated guess. Or maybe you've deployed a network based on a coverage map only to discover that the real-world performance is completely different. It's so frustrating, and that's exactly what we're here to talk about.
So what's the fix? Well, the solution is to build what we call the propagation bridge. This is the tool that connects the pure physics of electromagnetic theory to the messy, complicated reality of the field. And that tool is the propagation model. And we're not talking about a single, simple formula here. These are sophisticated tools that factor in everything: terrain data, buildings, atmospheric conditions, the whole shebang.
And this quote from the source material just nails it. It perfectly captures why modeling is so important. You know, this isn't just some academic exercise. It's the essential link that makes all our knowledge actually useful out in the real world.
Okay, so let's move on to our first case file to see how this works in a real-world scenario. We'll call this one ghost interference. It's a classic mystery that can leave even seasoned technicians scratching their heads. So here's the problem. You're monitoring a VHF broadcast. Normally it's totally clear. But then, out of nowhere, you're getting absolutely slammed with interference from another station, on the exact same frequency, a station that's supposed to be hundreds of miles away. So what on earth is going on? This is where having a propagation model is a total game changer. The diagnosis is a tropospheric ducting event. Basically, the atmosphere creates a temporary waveguide, like a tunnel, that carries the signal way, way farther than it should normally go. Now, you can't stop the weather, but the solution becomes crystal clear. You document the event, the time, the weather conditions, and just like that, a random glitch becomes hard data you can use for frequency coordination later on. All right, let's tackle another common problem, and this one can be pretty costly. It's time to open the case file on the mysteriously fading microwave link.
The stakes here are really high. We're talking about your critical point-to-point microwave link, the one carrying all that essential data, and it just keeps dropping out. And not just for a split second, but for seconds or even minutes at a time. The link budget said it was solid, but reality is telling a very different story. So why is this happening?
Once again, understanding the propagation model leads you right to the fix. The diagnosis is multipath fading. What's happening is a reflective surface, like water or even just really flat ground, is creating a second signal path. When that reflected signal arrives out of phase with the main signal, they cancel each other out. That's your destructive interference. So the solution isn't guesswork, it's targeted engineering. You install a space diversity antenna, or maybe you just reposition an antenna to mess up that reflection geometry.
Okay, let's pull back and look at the big picture for a minute. We've seen a couple of examples, but what's the fundamental shift here? It's about moving from a world of guesswork to one of engineering guarantees. Let's really look at what that means for you.
I mean, the contrast is just stark. Without models, you're dealing with hopeful guesses, coverage maps that don't mean much, and a whole lot of expensive trial and error. But with models, you get reliable link budgets, accurate coverage predictions, and frequency plans that actually work from day one. It's the difference between uncertainty and precision. And here's the real bottom line. Mastering these techniques just elevates your work. You stop being a technician who just reacts to problems, and you become an engineer who prevents them from ever even happening.
So, as we wrap up, the final thought here is for you. Armed with this understanding of prediction and modeling, think about the challenges you face every day. Which one will you tackle not with a guess, but with a model? Which problem are you going to predict and solve before it even starts?